Hello everybody and welcome back to the fourth part in our SCoBi Signal of Opportunity Coherent Bistatic Scattering Model tutorial series. This is the third example coming out of our user manual. We're going to be talking about a time series analysis as well as a root zone soil moisture profile analysis within this section. So this is the outline for this video. We're going to be going over the problem statement, again coming out of the user manual, and the geometry associated with this problem. Additionally, we're going to be talking about how to place this into the configuration input file in Excel, and then we're also going to switch over to the GUI window and show how to set that up within the GUI as well. So here's our problem statement. We have a root zone soil moisture profile, which means that instead of you representing the soil moisture as just one value, you're going to be having several values within that profile to represent the changes of soil moisture throughout that profile. This is going to be a bare soil analysis, which means that we're not going to be worried about vegetation. You can worry about vegetation if you want, if you obviously are traveling through some kind of vegetation canopy, you want to include that. But for this one, we're just going to assume that nothing's growing over the top of the soil. And in this case, we'll also assume that the transmitter is geostationary, nothing's moving about, everything's going to be fixed. And the antenna input is going to use the default generalized Gaussian input that is packaged in the GUI window. So we'll again walk through how to set that up. This is going to be a time series analysis, which is we'll show you how to set that up, and that's about it for that. So here are the inputs that you need to consider if you're thinking about a multi-layer problem or a root zone problem. First off, we're listing the root mean square height of your soil surface, and that's represented by this sort of squiggly line that we have going on right here. And that represents the roughness at the top of your soil moisture profile layer. Next up, we have the soil moisture probe locations. You can, and by that I mean we're setting up points within the soil moisture profile that function as probes. Because each of these points is going to have a volumetric soil moisture value at that location within the profile. Next up, you're going to have your air layer size, which is this in blue, and the soil layer size, or really the bottom soil layer size. I'll get into that in just a moment to try to make sense of that. So SCoBi has a few different ways to interpret the multi-layer problem. Off the top here, we have a second order polynomial fit, a third order polynomial fit, and a logistic function fit. And I'll talk about the discrete slab in just a moment, but to get an idea of the polynomial and logistic function fits, at each of these four values, we're going to have known volumetric soil moisture values at each of these locations. And with these different fit functions, what we're doing is we're applying some sort of polynomial that interpolates values at all the different other points within that soil moisture profile based on your user input. So as you can see in this figure over here, we have some volumetric soil moisture value that was located at 5 centimeters, which is represented by this little red bubble right here, another 10, 20, and 40, and the soil moisture was known, and you don't see that listed across the x-axis here, but that's because the volumetric soil moisture was converted to a dielectric or relative permittivity value at each of these points. So what our model has done, or what our simulator has done, it has again taken each of these points along this profile and has tried to make a continuous soil moisture profile that tries to match a fit for the four values that are listed. And that's what the top three do. I'll try to talk about the discrete slab in just a second. Now, I say continuous, but obviously your computer doesn't have an infinite amount of RAM, so infinite amount of memory in general. So what you're going to need to do is set up a series of points that functions as being essentially continuous for your problem. You need to have much more than what you need. So with this, what we're showing here is that we're generally thinking about the soil moisture profile in terms of centimeters. Again, we use 5, 10, 20, and 40 centimeters for this problem. And within our input file, what we've decided to do is label things as being discretized with a variable called del z. And what that does is it breaks the soil moisture profile up into components as big as the value that you input. So in that file, you'll see that it is 0.001 or 1 millimeter for intents and purposes of this problem. So at every millimeter down from the top of the layer down to the very bottom, there is going to be some value assigned for a relative permittivity value within that soil moisture profile based on that input. As you change that, you can change the, I guess you would say, resolution of your soil moisture profile, but that's just what we've chosen for the default input. All right, so a minute ago I talked about the, what was it? The discrete slab, this value that's listed here at the last bullet point. So let me see if I can make sense of that real quick. So a minute ago, we mentioned that you needed to mention the size of your air layer, and we're going to denote that with ZA. And below that, I'm going to get a different color right here. We're going to make it orange. Let's just say that we have a big old block that's representing our soil moisture profile. And at the start of it, we have Z equals 0. And at the bottom, we'll get into how we define that in just a moment. And let's say at, again, I'll change my color here. At this point, let's say that's our 5 centimeter value. At this point, let's say it's our 10, 20. I know this isn't exactly even. And we'll say this is 40. Yeah, that's definitely not even, but you kind of get the idea. All right, so with a discrete slab function, what that fit does is it assumes that because you only have 4 soil moisture values, each of those values is going to represent a piece of the soil moisture profile. And what it does is it takes the midpoint between adjacent soil moisture probe values, or I believe the input calls it. We'll check that out once we go into the Excel file and look at it. But between each of these points, so the midpoint between 5 and 10 is going to be 7.5. And this is all in centimeters, by the way. We're assuming everything's in centimeters. So between 5 and 10, we have a division of 7.5. Between 10 and 20, 15. The midpoint between 20 and 40 is 30. And at the very bottom, one of the inputs into the program is something called ZB or ZBottom. And what that does is whatever your input is, you're going to add that to your last soil moisture probe location. So for our default input, that is 30. Sorry, I need to erase this part because this is coming from where this 40 value is. So we're going to say that from here to here, we have 30 centimeters. So the very, very bottommost portion is going to be 40 plus 30, which means that our total soil moisture profile extends down to 70 centimeters. Okay, so with all that in mind, what the discrete slab function does is it assumes that whatever volumetric soil moisture was at 5 centimeters beneath the soil moisture profile, well, whatever that was, that is the dielectric of this whole slab. It's now a 7.5 centimeter chunk. And then for the next layer, the one at 10 centimeters represents the soil moisture layer between 7.5 and 15 centimeters, and so on and so forth all the way down. So that's what the discrete slab is doing. This kind of describes both the air layer size, which I think for this default input is 10 centimeters, if I'm not mistaken. In this problem, for the discrete slab, you're not going to be using the layer discretization. I believe I'm saying that right. which again I think is 0.001 or 1 millimeter. I apologize if I'm not getting that right. I apologize for continuing to erase that over and over. But yeah, so del Z, or the layer discretization, isn't used at all for the discrete slab fit. It's used for the different polynomial fits and the logistic fit functions, but for this, you're assuming large chunks are the same soil moisture value essentially. So that about does it for this portion of the tutorial of trying to visualize things. For the next bit, we're going to input things into the GUI itself, and well, actually before that, we need to set up our Excel input file. So I will see you guys at that portion of the video. Alright guys, I'm back and ready to take a look at the configuration input file for this simulation type. So we're going to go back into the source folder, take a look at our input files, go into the configuration, and we're going to be looking at, since this is a time series analysis, we're going to look for things with the TS timestamp. It's a multi-layer and it's geostationary. So we're going to click on this guy right here. And this is our Excel input file, the configuration input file. Again, this has two sheets: the dynamic sheet, which represents values that change, or either, since this is a time series file, it changes as a function of time, and the ground file, which is things that remain static. The names of these sheets don't matter, but their position does. So if I switch this guy over here again, not good. So keep that in the initial position. And again, these row titles don't matter. I can erase this and make it whatever I want, but that's all for you. Everything in SCoBi is dependent on position, where the columns are located. So just keep that in mind. So since this is a time series analysis, the first thing that you're going to be seeing in your dynamic input sheet is the time series function, or the day of year column. This is going to be the rate at which time changes. Honestly, you could just put, 1, 2, 3 all the way down if you wanted to, if you weren't really necessarily needing something that was very specific. But generally, for our data, we've always used the day of year notation to try to keep things in line. So that's what this first column does. That's what's different between a time series and a snapshot mode analysis. The very first column in a time series analysis is going to be your day of year column. So since the RMS height of the soil moisture profile is the same throughout everything, we just have one value up here in cell B2. So that means the RMS height is 0.5 centimeters for the entire test, which is this. This is a very large spreadsheet. You may have noticed back over here there's a simple version of that I included because I was trying to run a few tests, and this computation, I think it took a little over 15 minutes for me to run, just because of how many inputs there were, but I can't quite remember. It was something like that, and I needed to shorten it a little bit. Anyway, so those two values, the time and the RMS height, are your first inputs, and the rest are your soil moisture probe locations. Again, these names don't have to be these, but they are indicative of what's on the ground sheet that we're going to look at. So each of these are percentages of the volumetric soil moisture. So this is 37% volumetric soil moisture in this column right here, 33%. And as time changes, so do these values. So that's it for the dynamic sheet. In this case, again, you have your time value, the RMS height, and the values of your volumetric soil moisture. But that's largely due to this being a geostationary satellite. If we did have a geostationary satellite, we'd have two more columns right at these positions defining the theta and phi values for the orientation of your transmitter. So hopping over to the ground sheet, we have the layer depth. These correspond directly to the dynamic sheet. So here, since these values are in meters, 0.05 is 5 centimeters, 0.1 is 10 centimeters, 0.2 20, 0.4 is 40, and those correspond back over the dynamic sheet for these columns. So the first row right here is representing the first series of multi-layer soil locations for your dynamic sheet. So that's that. And the rest is mostly the same that you've seen up to this point. The sand ratio, defining how much sand is at this location, or what percentage of sand is at that location in your profile. Same for clay. Your bulk density is represented by this value. And then, as we talked about a minute ago, these are your del Z, your layer discretization, and the size of your air layer and the size of your bottom layer. And one more time, just to try to get that across, this plus this guy is going to be the very bottom of your soil moisture profile. So this particular one extends down to 70 centimeters. If you feel like you need more, feel free to change this guy to be a little bit more. But otherwise, that's really all that you need to know. So with all that in mind, we're ready to go into the GUI input itself. All right, everybody. So now we're ready to take a look at the inputs for our root zone soil moisture profile. So I'm going to go over here and give run SCoBi.m an old run. And we're going to go over here and click on the root zone simulation to try to pull those values up. I've got the default root zone inputs file loaded, which you can do that from going over here and clicking on default root zone. I've already got that, so I'm not going to worry about it. Again, this is a time series, and we're not worried about vegetation, so that's why those values are there. For this particular input, we're including it with a master simulation so that you can kind of visualize how that output is going to look whenever it's in a master folder within your output of SCoBi. Coming over to the transmitter inputs, we see that our transmitter is at 370 megahertz, 42,000 kilometers away from the center of the Earth. We're not really interested in rigorously defining the effective isotropic radiated power of this specific transmitter, so we've left it at 0, or maybe it is 0 dB. Not sure. Either way, both of those cases work. Our polarization is right-hand circular polarization. Our orientation is geostationary, which means things are fixed, and this is the value that we're keeping it fixed to. Our incidence angle is 40 degrees, and our azimuth angle is 0 degrees. Our ground input, we're going to assume, is a Dobson soil moisture estimation. The ground structure, again, is multi-layered, and you can click on as many of these as you want. Obviously, the more that you click on, the more calculations that the program is going to run. So do what you will with what you'd like in that regard. The receiver input is 20 meters. The receiver input for the altitude is 20 meters off the ground. Gain is 0. Polarization is vertically polarized, or X polarized in this case. X polarization is perpendicular to the ground, so it's vertically polarized. Our orientation is fixed at the 40 degree and 0 degree incidence and azimuth angles. And again, our antenna input is a generalized Gaussian antenna pattern. We got our beam width, or half our beam width being 30 degrees. Our side lobe levels are 30 decibels down below that. Our cross polarization level is 25, and our pattern resolution is 1 point for every 3 degrees. And we have our configuration inputs file linked, the one that we were looking at just a minute ago, linked to that Excel input, which was, let's see, right there. And there you guys go. That's all you need to give this guy a run. So once you hit run SCoBi, you can save that. Doesn't really matter what we save that as. And that's how everything's going to look. So I hope that tutorial was helpful for you guys. If not, again, shoot us an email, leave us a comment, and let us know how we can help you guys in the future. Thank you so much for watching, and again, we're looking forward to hearing from you guys.